All right. So, not playing a game today. I'm going back to that Chip8 emulator I started. See if we can get further in that. Uh, Fortunately, I didn't leave myself very good comments last time. And again, didn't really get much done. It sort of runs some of the uh, opcodes. However, that's about it. It does load stuff at the right spot, which is nice. We're not handling any input yet. That's something that I'll have to get to. I need to actually source some Chip8 ROMs. I didn't actually do that before I started. But that's fine. I don't think we're going to get that far today. Oh, I should also start. Abuse 1 second. It should be. There we go. I have some really quiet noise in the background. So, looking at this again after a while, there's probably some renaming I can do. I also need to get a display library, where's cargo? Yeah, I haven't put anything in here. So I'm going to need a library to display stuff. I did look some of that up. Pretty sure it's FLTK. And I think there's a library called Pixels to draw basically arbitrarily sized quote unquote pixels to a screen, which seems really convenient. So I'm not going to add those in yet. I don't think I'm going to get to actually displaying something. Oops. This is code. This is cargo. Just leave those in there so I know to go back and look at that. All right. What was the document thing? 3 backslashes is all I was using. Great. See if there's more to it. It's not clear what that actually applies to. Let's see. So they suggest triple lines and then what's the equivalent? Okay, that's outer. Which can also have 2 asterisks. There we go, that's a multi-line. But it doesn't matter, we'll get to that. That was just good to look up. Okay. So this instruction. I don't like this. This is just yelling Chip8 CPU everywhere. We'll just call it CPU. And it's gonna hate me for it because I was supposed to rename it up here. There. Okay, I could go through more of the instructions. Might be a good place to start. Yeah. So where did we leave off? Actually, we don't need cargo open. Left off at 7, 8. Whoa. Double clicking apparently brings you back to where it's defined. That's good to know. AXY0. Store V. Y into VX. Actually not going all the way to 8 F because the last digit's always 0. So technically, there's a few more invalid opcodes there. This is store register? No. Did I have all the instructions written out? No, I didn't. Add constant was the last one we did, right? Yep. Okay. So add a constant. This should be store register. This should be store constant. Because we're going to store a constant into a register. Ooh. Ooh. Go. Comma. That's not even right. It's X and Y again. Comma, go back up here. Store register. Wondering if I should split some of this opcode manipulation into some functions. Because we're doing some similar stuff in a lot of this. Let's do okay. So all of these are taking that. So, oh, need to add. That one's easy enough. Store value of register Y and register X. I was going to do something. Functions. All right, just take this from where I'm looking. Okay. What do I want to call this? We're taking... the second nibble as a register, I guess. So this takes a... I guess we could call it source. It might not be an opcode, but actually that's all we need. And it's going to give us a U size, and all it is right. It's not U size, so we have to cast it. There we go. There might be a better way to do that slightly more generically. Actually, let's take a look here. So registers are always the first or second argument, right? Or nibble. Yeah. And there's never one with 3. So would it be decode? I don't really like putting the name in there like that. Actually, can I implement something on U16? So then I can just do like opcode dot to register X. Is that valid? Can I do that? Let's find out. Simple. It doesn't like that I'm doing this. No. Alright, consider using a trait. E0, 390. Let's just see what that says. Okay, so a way around it is to make a structure with the thing in it. I don't really like that. Actually, why is process in here? Why does it not like process in here? It doesn't really say why it doesn't like process in there. Okay, so I can't add an implementation on it. At least not cleanly. Could make a trait for U16. Well, that would... then I have to pass it around as that trait. So, no. We're going to do this. Actually, what are we doing? Source and... not in scope. What am I implementing? Is it just CPU? Yeah. Nope, that's wrong. Self.register X? No, it doesn't like that. It's a good way to do this. Oh, I do need that. Yeah, there's definitely a better way to do this. I just can't think of it right now. I'm actually ran a trait. Function. No, I don't think I didn't send this out. Dummy. I keep doing that. Did I even do something about... Yeah, I did send that one out. Okay. Row that out onto the internet. Okay. So, trait register. No, trait opcode. Yeah, that'll make more sense. So function register X. What else did we get? There's a lot of getting the second byte, which is generally what? Implement opcode U16. It's just missing functions. Okay. Let's start with one. Let's prove it out first. Just to make sure I'm not being a dummy here. All right. Don't need to pass the type to self. Mismatched types. Oh, because I haven't implemented it yet. Where did I go? Self. Okay, what's wrong? This feels weird. Okay. That was on skip equal constant. Let's also make sure that works. Skip equal constant is 3003 FFF. Okay. Load FF into register 0. If register 0 is FF, we skip. Right? We're on skip equal. Yeah. Which means we won't do this. Just quit. No, we want to quit. So if we skip, we will, if we don't sit, we will set register 1 to FF. All right. Go run. Oh, that is great. That actually looks really clean. Okay. And what we were doing here. This is now self. Oh, right. None of these actually defined a return. The constant byte is a U8, and the triplet is a U16. Constant byte, triplet. That actually takes care of almost all of this. If only I thought of this sooner. Okay. I can't really leave a comment without having that uncommented. That's fine. We will implement both of these. Fortunately, these are all in consistent locations, which I just didn't realize before. So yeah, I think this is all the functionality we need to actually pull data out of an opcode. Just need to finish implementing it. All right. Constant byte. As returns to 8. What was I doing? 2 big endian bytes and get the second one. Self and OXOFFF. All right. Well, let's constant byte. All of the single registers are a register X. I should really start writing some tests for this so I don't have to go and constantly tweak this just to test out something, because this is a massive sweeping change. Y. These are constant triplets. Well, let's just make sure that this builds and runs. Okay. Which also means store constant worked as expected. And exit delete this did as well, but that's not actually using any of that. Oh yeah, we also have stuff here that's not implemented at all. The stack's just kind of pushing it over. I am going to need to look at the stack, but not right now. Okay, that's a little better. Oh yeah, and the program counter jumped over 204. That's all that proven out. Okay. Testing. I believe you make a test mod For unit tests is the recommended way to do it. Here we go, automated tests. Yep. Okay. There's probably a way to separate it out, but that could be done later. Let's do the ones that are actually implemented. Starts at skip equal constant. Oh. Can I just, wait. The struct is right there. What do you, is it super? Ah, it's super. Okay. We have a new CPU. Load ROM. Actually, we only need to load the one because we're actually going to call execute. Hopefully we can call execute. Oh wait, it's public right now. Yes, we can call execute. Okay, load ROM. A vector of what is skip? Skip equal constant 3000. So 0 F what are you complaining about? Takes 2 arguments, but one was supplied. Oh, we need to give the location, don't we? Yep. Execute one instruction. Yeah, we need to do the full thing. Fetch. Returns the U16. Which this is. Well, decode. This should all be wrapped up in a single, like, step function. Just do the next step, which will do a full fetch, decode, execute. Okay. Insert equal. We want the. Wait, which goes first? Your stuff goes first. The expected is second. The expected is 200. Skip over 202, go to 204. Now this should take place as part of a build, right? No. Cargo test. Oh boy. What did I do here? And round bytes. Okay. I don't think I can just drop an ampersand there. Copy this out. If it's not clear, I really have no idea what I'm doing. What's wrong? Can't borrow as mutable. It's not declared as mutable. It is now. Hey, it worked. Have empty pair that it's skipping, and then I also want to test that it's working normally. Which I can just use the same ROM, reset the program counter, set that back to 200. Then, okay, yeah, I'm just gonna put step in. Actually, it doesn't return anything. What's wrong here? Oh, right. That's the next op code. Then next instruction. Decode. Next op. And then execute the next instruction. There. Now we can just tell it step. And we can get rid of this. Skip equal constant. This is just skip if it's equal to that. So step, it should not skip. I'm just going to explicitly set that. Right, yeah, we're working with register 0 equals 0. And step. Well, let's see what happens. One of these is wrong. Am I dumb? I mean, yes, I am, but what is going on here? Before and the after. So that again. It didn't print anything out, did it? Is it not running those? Function is never. That's why. Wow. Okay. Failed. Insertion failed. Left equals right. Left 514, right 560. Okay. Uh, 184. So this is skip equals, which means I wrote this backwards. This one should not skip. This one should skip. So now the tests pass. Okay. Get these out of here. This is I should really have tests like this for all these. Yeah, okay. So skip not equal constant. Fortunately, that one will be easy. It changes to a 4. And swap the expectations. Easy as that. One test, what? Oh. I didn't copy the testing notation. 2 tests. Look at that. We have test coverage. Wonderful. Alright, skip not equal register is also going to be relatively simple. Actually, all of these are. So we just need skip not equal register. It's 5 XY0. 5. Skip not equal constant. Wait. Editing the wrong one. Should also change the comments so they line up with reality. All right, skip not equal. So if they're not equal, it should skip. If they're equal, it should not skip. Okay, register 1, register 0 and 1. Zero and FF. Skip. Both FF and should not skip. Look at that. 2 passed and 1 failed. Skip not equal. So these are not equal. Should skip. These are equal. Should not skip. What happened? 220. Hmm. Skip. Wait. It's called skip equal, not skip not equal. Wow. Okay, not skip. This should skip. And that's why tests are helpful. What's it yelling about up here? Step is never used. Stack is never read. Well, stack's right. Step is about to be wrong. Just step. Let's make sure that works as expected. Cargo run. Still works as expected. Where is it printing that out? In fetch? And no. No. Do it there. Nice. That's better. Okay, so that was skip equal register, and now store constant. Like whatever, we can just copy this whole thing. All right, and store constant 6x and n. Do register 0 again. Test loading. F into register 0. There's not much to comment here. Step and then assert that register 0 is FF. Oops. Test. Okay, that was store constant. Add constant. This one I actually do want 2 cases on. So test add constant. That is 7 x and n. Register 0. We will add 1 to register 0. We will explicitly set it to A. Expect B. Because this one, it can overflow, however, you don't want it to set a flag for overflow on constant addition. So AFF, but we expect it to be reset to 0 after adding 1. Explicitly set. Whoops. I mean, I can also just actually write out 15, but it is hex. Okay. Clear it to 0 before testing, just to be sure. Who knows if I mess with the initialization later. All right, let's add constant, store register. This is 8xy0. 8. After it runs, it should have the same contents as y. Simple enough. These tests are getting long. Okay. All right, now we're getting into all the math stuff. So this is OR. It's always with the register. I think it's always with the register. So we can just call it OR. Bitwise OR. Oh, I didn't. Yeah, it would be nice to have the right, that's 7. Yes, the store register is 8. This is XY1. Where's it stored? Okay. Vx is set to the bitwise OR of Ex and Vy. Oh. I can't just directly match here. All right, I've got it. So match that. And then in here, match opcode, and it's ampersand, not multiplying. Match the last thing. Expected a comma. What? Unnecessary parentheses around. Whatever. Okay. Oh, right. I need the store register. It's not exhaustive. That is opcode. And this is where the testing is really going to help, because this is a bit of a change. One is bitwise OR, where register X and Y are this. Bitwise OR. All right. Test for it. So we will have OF and FO, or together should be FF. And let's see everything break. Oh my god, it worked. Wow. What? I was expecting something to be wrong there. That's great. Is there anything else I should put in here? I mean, I guess I could have a case where, like one digit overlaps. I mean, F8 and OF. But, I mean, it's bitwise OR. Oh, I would expect it to work just fine. Okay, that's bitwise OR implemented. Next, bitwise AND, which is almost exactly the same thing. Oh, I need to add it to the actual instruction enumeration, which, yeah, just copy this. Actually, even copy the comment. There's so little that has to change. So, continue. It's an ampersand for bitwise and it's bitwise and. It is 2, right? Yes. We're going 2 through 7 for all the next instructions. For the last nibble of all the opcodes that start with 8. Alright, bitwise and just copy this, because it's using the same thing. And we're just gonna copy this, because we are changing one instruction. This is now an ampersand. Down to the tests. Okay, so now we're anding them together, so this is actually going to be, oh wait. Right? Am I doing my math right? No. Left was 255. Really? What? No. That can't be right. And, oh. Dude. They're still doing OR. There we go. We're churning through some of these. Okay. Next. Exclusive OR. Alright. That's a 3. It's a caret for the symbol. Is XOR. And I mean, we're going to copy this because then we only have to change 2 characters. 3. And, oh, we have to change 3 characters, sorry. We have to lowercase the O and add an X. All right, and make sure that is doing things right. So bitwise exclusive OR with FA and OF. It's going to be F. Hold on. 8. So we have 1, 2, and 4, which is 7. I didn't change that to a 3. There we go. I can do exclusive ORs on small numbers. Excuse me. Wow. Okay, that's exclusive OR. 4 is addition. So let's add that in. Let's add constants. This is add register. And copy this in. Register X and Y again. Or why am I typing this out? I could have just copied this. Although there is actually more. Because we actually account for overflow flag in this. Or, well, I believe it's called carry. Same thing. If the 2 numbers would be greater than 255, the number rotates back to 0. Well, it just rotates, and we set the carry flag. So it's just another one with 2 registers. 4. Add register. This one's actually going to be slightly complicated. So I'll do brackets around it. What's wrong here? Unused. Okay. Let's see how awful this looks when I do multiple bits of code. So let equal B register X is that's just add 0. And then now this is hard coded and how it works. So don't ever use register 15 as register X. Otherwise, this is going to happen to you. Yeah, it's just going to be 1 no matter what. Actually, no. I need to look up what does overflowing head return. Is it a Boolean? Actually, is there documentation for it? No. Overflowing add. Okay, it returns a Boolean. So if add dot one lovely. Definitely going to want to test this one kind of thoroughly, by which I mean one that overflows and one that doesn't. So this is now 4. So register 0 and 1. I add 01, 09, I should get A. I can count to A. Reset the position. Right, insert, oh. That's right. It's explicitly set to 0. If it is not. If it doesn't overflow. So register 15 will always be overwritten on an add. There's no overflow. Register 15 should be 0. Program counter back to 100. This time we do overflow. So easiest way is set that to FF and well, just add 1. We step, so the result should be 0 and then carry bit set. Test. I can't believe that worked. 1 second. All right, so that's add. Next is what, subtract? It's subtract. Which, I mean, I guess the VF isn't really being used for flags, except for a very weird definition of flags, because on subtract, VF is set to 0 on borrow, and 1 if there's no borrow. So it's not that there's a borrow flag, it's that you expect there to be a 1, but if there's been a borrow, it's a 0. Which is odd. To me, anyways. I'm going to call it subregister, even though I don't think there's a constant subtraction. This is 5, right? Yes. F equals subtract. F equals 0 on borrow, 1 otherwise. All right, VF equals 1 on carry, 0 otherwise. That's a bit more explicit on how this works. All right. So we have for 5, register, and operands are the same. Subregister is just going to be a whole mess. And I need to look at, I guess, underflowing. Subtract. I guess it's still called overflow. So overflowing sub. There's a phrase. All right, so subtract. Register X is the result. And if we want to reverse this, if there has been an overflow or it's underflow, or hopefully, well, we'll see how it works. So copy this test. Test sub. No underflow and underflow. Well, if we take A, subtract 1 from A, obviously that's 9. Then there should be borrow. Here, let's start with, well, 0 and subtract 1. Oh, I should set that bit. 0, subtract 1, so there was a borrow, so that will also be 0. And I expect this to explode. Yep. Right was 0. At 380, it was 0. Expected 255 because it should have been 255 because we underflowed. Sorry, FF. Yeah, CPU 0, 0. Subtract 1, underflow to 255. Yes, that's correct. Okay. So the code was right. I wrote the test wrong, which is concerning that this has been going so well. All right. Next is shift right. And we just shift right 1. Okay. X is set to Y shifted right 1. F is set to least significant bit before shifting. Right. Shift right. Register X and Y. X, Y, 6. All this is saying is that VF is going to contain the bit that was shifted off of the register, since it's not a rotate. Rotate would just wrap the bit around into the same register. Shift, it just goes away. Okay. So 6 is shift right. Same operands. I believe for all of the math ones in the 8000 series. Add shift right. Add shift right, right. Although it's going to be complicated. Actually, yes, it's going to be complicated. There might be a way to like golf this down, but I'm not going to do that right now. So solve that. Let's see if we can keep this simple. And solve that the F register Y just ANDed with 1 to get the last bit. Okay, that's that. I think we can test this pretty easily. I don't even know if that's the right bit shifted off. Whatever. I understand it. That's all that's important. 6. And I mean, if you read what it's doing, it'll hopefully make sense. All right, so no bit shifted off. 8 is the 8 is the most significant bit of that nibble. So if we shift it right, it'll be 4. Oh, wait, no. Y is the one going, and Y is register 1. Register 0 is just where the result's getting stored, so we'll just clear that to 0. So afterwards, it should be 4. Register 0. And F should be unset because there was no least significant bit. Now, reset, and we'll just set this to Nope, it was exactly right as it was. Set to 1, because then there's a single bit, and it's the least significant bit. X should be 0, but there should be a 1 in VF to let us know that it was shifted off. Wow. Okay. We're on a roll. So that was right shift. Next is subtraction. Oh. What do I even want to call that? Like, okay. So this is okay. So X is set to. Okay, where's the one that's comparable with? Oh, right above it. XY5. Okay, so this one is register X is set to register X minus register Y. This is register X is set to register Y minus register X. So I called that first one subregister. I could call it subregister Y. Then you're subtracting register Y. And this one could be subregister X. You're subtracting register X. Or do you do that for the source? So subregister X would subtract from register X, where subregister Y would subtract from register Y. And now I'm just confusing myself. So I'm just going to pick one and go with it. And it has the same carry logic. Subregister Y. That's where we're going to go with that. We'll change that one to subregister X. Now everything up here is broken. Is this the last one? Oh, right, we have E. Because we go from 7 to E. Whoop, nope, this is not a shift. This is sub register Y. And all the same operands again. Okay. Now down here, match the instruction. We need subregister Y. Why am I making this complicated for myself? Just copy and paste. Just register Y and register X. Self.register X. Yep, we're still setting in X. Right? Yes. Yeah, the more I think about it, the more this doesn't make sense. Why this instruction even exists. Because you could just write it. Alright, so you have, where is it? Subregister X. So this first one, 8xy5. So say you want to subtract register 1 from register 0. Like we were doing in tests, you would do 8015. Now, instead of doing this 8017, you could just write 8105. It would store it in that first register, but I honestly don't see why that's a problem. Whatever. It's implemented. Now we test it. Where's up here? Let's add constant. Subregister Y, subregistery, subregisters. right, and 7. Okay, so we are subtracting register X from register Y this time. So we just need to swap these around and it should give us the same results. And it does. Weird as that instruction is, it's done. AXYE is left shift. Schleft. And we're just using the same register X and Y. It's all the other math operations. It's Y, E, E, X, E, Y. Shifted left. Nope. Shifted left by 1. F is the most significant bit. For the same reason as it is in right shift, only now it's the most significant bit, because that's the one that gets rolled off. E. I can spell. You know what? I'll let it spell for me. Why am I fighting the duel? The logic's pretty similar, so I'll copy this in and mess with it. Most significant bit is 8. Well, 80. And then we just left shift. Get out of here. Shifting left. We'll take this and change it to testing shift left. Test shift left. Great. And this is E. So no bit shifted off. 8 will roll into 10. I can count. Makes sense in hex, all right? And nothing is rolled into the flag. Okay, this is going to be the opposite. Where we have 80. And that gets rolled into the flag and set to 0, right? No. Wrong. Left is 128, right is 1. Where is this? 469. Left was 128. Oh. I'm not sure if about the wording on this. Should VF be set to 1, or should it actually be set to that bit? So I'm going to assume 1 for now. And when I actually start running ROMs and they blow up, that could be one of the problems. So down here, excuse me. We need to shift that right 7 times. Try again. Okay. Oh, is it skip register not equal? We're back to different things. Keep our wording the same, skip not equal register. And it takes 2 registers. Imagine that. Alright. And this is 9xy0. Which means we're also out of this mess. And this is using the same thing. Simple as that. Register X does not equal register Y, program counter plus 2, which skips the next instruction. Actually, wait, I have a test for skipping. Yeah, test skip equal register will now be test skip not equal register. Look at that. 9xy0. 9, register 0, register 1, 0. Register 0, register 1, not equal, should skip. Equal should not skip. So it should skip, so it should be at 204. It should not skip, it should be at 202. Another instruction down. And store n in I. It's a store constant, but store constant index, because it's a separate. Yeah, store constant the index because it is labeled as I. Wait, no, there is no register. There's just the value. I am typing something. Okay. Store the constant n in I. So constant triplet, because it's 3 nibbles. And if you didn't know, it's called a nibble because it's half a byte. Oh, that's the error there, which is expected. Store constant. I can spell store constant index. Value. This one's real easy. Self-deny equals value. But mismatch types. Expected usize found u16. As usize. Fine. Right, because I is index, and it's indexed into memory, which means I need to use a usize in order to access it easier. This should be relatively simple to test. What am I doing? And we'll store F. Fab. Oh, you don't need V at all. We'll just explicitly set this to 0, just in case. And then step. Okay. Jump to address v0 plus constant. Okay. 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 B is, what would you call that? Jump offset? Call it jump absolute. Yeah, jump offset. What does that take? Uses register 0, so it's just the constant value u16. Similar. Let's go B to B. Let's jump offset. We handle it down here. What did I do for jump? Did I just explicitly set the program counter? I didn't do anything. Okay. Should really be writing that out in hex since I'm doing all the addresses in hex. Plus, let me guess. Expected usize found U8. plus value as usize. There. And I should probably also add in a test for the jump absolute. So here we go, test jump offset. The do FOO set B 0 AB step, and PC should be at AB. Excellent. Back here, let's implement jump absolute. Why is it printing a line? It's easy. Return and call haven't been done because I haven't messed with that yet. Using the stack, I should add in a stack pointer as well to know where we're at in the stack. Anyways, jump absolute. WC equals address as usize. Yeah, this should be called address. Because we're going from a relative address. Okay. And jump absolute is, yeah, here. So copy this. Go all the way up to the top. All right, I think tests are the majority of the lines now, which is fine. Wait, what is jump absolute? 1. There doesn't matter, so we just step and we assert that we are at FAB for the program count. Yeah. Didn't rename the function. Excellent. 18 opcodes tested. Where are we? Okay, that was jump offset. Next is random. I don't know how to do random numbers in Rust. Guess I'll have to find out. Okay, set X to a random number with a bit mask. Takes a register and a mask. No, the mask is an 8. Up to 16. Is random numbers in the standard library? It is. It looks a little weird. Random. Alternative, you can use thread RNG. Well, let's just look at random. This is a shortcut for thread RNG gen. Okay. Following types of implemented. So, okay, we can get a random U8. Perfect. Random. So now we need to get it. And comma. What's wrong with... Oh, right, it's called mask. What's wrong here? Failed to resolve rand. This is in... Is it STD rand? What is the actual... I was in a random... I was in a random crate. That's not helpful. Oh. Oh. That's the recommended way to do it, is to use that crate. All right. So, cargo. What version's it at? 085. Waiting for file lock. Why is that taking so long? Okay, so we have the library. And it appears I'm using it right. Which I could just import random. And then just call random. Okay. And let's test it out. How are we going to test it out? Here's the problem. I can't can't, I can check that the mask works. I can do that. But, I mean, the number could be anything. If I don't even use a mask, just set it to FF, I can't even check that it's not 0, because, hey, the random number might be 0. So... I guess I'll test the mask. Are there other assertions? Like, can I test? I can print CPU at the end. Fine. Okay, so C register 0, and we'll take a full number. So we can't even set, it's gonna be set to something. So we'll step insert. Yeah, you know, no assertion, just run it. Because what the heck? Didn't print anything, did it? No, what? Why didn't it print anything? Okay. So for testing this, we may have to get a little odd. Maybe? Okay. So to be able to test this, I need to use a seeded RNG, which means I need to set an RNG. You know what? That might not be the worst idea. That might be fine. We'll have an RNG on the CPU. You can set the seed on it, or it's just seeded the same at the start with some default. So what's a fast one? Small RNG. What is this? I have to look at crate features too. This is kind of a pain. Seedable, because that's what I need. It does. Well, here's the thing. We're using U8s, so it could be a number 0 to 255. Basically, as long as we don't use a really bad RNG, we're fine. All right, whatever. Well, can do anything that's seedable, honestly. So, where? Let's implement seedable, right? Yes. Okay. So to do this, we need. So the CPU is going to have. Which I believe is in here, right? Oh, what's going on here? Oh, the structure is blown up. Y value. Wait, what? Um, okay. There's something going on here. You know what? We'll use Chip8 just because. There you go. It is in a different part of the crate. Where is it? It's in Rand. Supposedly. Unresolved import. It's in here, isn't it? It's a dependency. Yeah. But because I don't have... Pull in whatever we're using. Wait, no. Who would have thought I'd get hung up here, just making a random number. So, hold on. Alright, so if nothing is set, we go from entropy. Right? Right? If I'm reading this right. Creates new instance of RNG, saves via. No function found. No, we don't need the other one from RNG and pass it yeah. Cannot find thread RNG in scope. That's because we need okay. Whew. This is getting complicated. So where's random? So now we don't do that. We do self the RNG. That's Jen, but yeah, that's not doesn't implement that trait, does it? No. Does RNG core, which... Alright, enough messing around. Next, U32. Can we get the last bite of that? I mean, 16 had two BE bytes, right? Yeah. 2 BE bytes. Grab the third one. Or grab the first one. Or just grab one. And throw the mask on it. Perfect. And now, down here in the test. Oh, okay. G equals. What's that from? C from U64. 0. Colon. Right? What's wrong here? Oh. What? There. No function, seed from U64. Bound for Chip8. Items from traits can only be used if the trait is in scope. Well. What is seed will RNG in? Brand core. Which is not cargo. Star. It is now. This has been a journey. Yeah, let's just... What's wrong here? Oh, I need to give the format. There we go. Just imports everything, I guess. What's the number we get? It doesn't really run the test, does it? Nope. Okay. Why doesn't it print anything? Is it because there's no assertion, so it just doesn't? Oh, man. Okay. So we'll insert that. The B0 is 0. Just we'll just make that assertion. Yeah, it was wrong. All right. So it's going to give us A7. Masking it with FF, so it'll just be A7, which isn't interesting. We will give it a mask of F0. Then assert that it is A0. Right? Oh, okay, run it a few more times. We're good. That will always be A7 for the first byte. Okay, random numbers tested. Don't ask why we're using a cryptographically secure random number generator, but here we are. I honestly probably should just implement some sort of simple random number generator in the CPU. That was more effort than I would have liked, just to do some random numbers. Okay. Draw a sprite. That one's going to be stubbed out right now. Draw a sprite. The D, X, Y, N. N is the size. Okay. Wait. Draw sprite of X, Y, that is N bytes long, starting at I. So it is drawing a sprite and collision detection. Oh, and we're going to need another function on opcode to get the last nibble. I guess it could be a U size. I don't think anything else uses it, so U size is fine. Okay, so right. Okay, draw sprite. I will just copy a register X, register Y, because that's 2/3 of it. The size is dot. Constant nibble. And stub it out. Oh, haven't given it any. So that's going to be Mr. X. Register Y. Oh, just size and self.I. All right. So stubbed out drawing is bright. That's going to be complicated, and we'll do that later. Skip the next instruction if the key VX is pressed. Right, we need to handle inputs. And making sound. Although I can do the sets and read instructions just fine. The real thing is going to be actually making sure they count down and produce sound, but yeah, so skip if VX is pressed, skip if VX is not pressed. Right. EX9E specifically. Oh, why does the X have to be there? All right, there are only 2 instructions that start with E. So I can deal with that. That's fine. So it needs to know key presses. And that's all we need to know is if a key is currently pressed or not. So I'm thinking yeah. What's wrong? Oh, yeah. Initialize it to nothing, I guess. I'm sure there's a some sort of bit thing I can do, but I mean, why? Why worry about that right now? Let's get this thing working first. So that's actually going to have to come from input somewhere, which is another thing I'm going to have to do. Is handle it, key presses, and figure out what I'm going to use for keys. Because it's a 4x4 keyboard, which is kind of odd, but it was a hacked keyboard, so what can you do? Okay. That's all the keys. Did I add it here? No, I didn't. So we'll handle all that. There's only 2 valid bytes for the end. If this is kind of ugly, but what was this one? 9E. This is a skip E pressed. Go register X. And just so I don't have to go back and forth, the other one is A1. Otherwise, invalid opcode. Okay, not as bad as I thought it was going to be, because I can just match on the last byte. Still not great, but whatever. The actual implementation. Skip key pressed. Whoops. Don't even know if I have to go that far. Register. If What's wrong here? Cannot be indexed by U8. Oh, that's fine. We'll cast it to a U size. Cannot be indexed by U8. Oh. Right. We'll cast it to a U size. We'll cast the right thing to a U size, which is fine, because it'll be less than something that'll be out of bounds. It's unsigned, so it can't be less than 0, so it'll get us something. Then easy plus equals 2. Amazing. What's wrong up here? No method named get BE bytes for U16. Two BE bytes. There we go. Fortunately, I can still test this. Grab skip. All right, test. Skip key pressed. Key pressed. Skip. Key not pressed. Don't skip. The X is not key. What do? All right, we'll get to that when we burn that bridge. That's the phrase. Wow. And 9E. E090. Okay, so 0 will be A. A is a key. Did I call it key or keys? I called it key. Yeah, that's fine. So it's true, so it should skip. And now, just copy that, paste it here. False. We do not skip. Now we do it again. BX is not a key. Current implementation is don't skip, but I'm not sure what to do if it's I mean, it would check for that key if it's pressed, like if you did this in hardware, but there would be no key to check. So false, which means don't skip? Question mark? Just to make sure that it's skipping, even though, I mean, whatever. Yeah. That's good enough for me. Don't skip if it's not a key, because you're checking for a key that doesn't exist. So of course it's not pressed. And to keep that consistent, of course the key's not pressed. So when we do the negative version of this, it will skip. So don't skip. 202. This should be 204. And this should be 204. Key not pressed. Skip. Skip. Question mark. What was I doing? Not that. Oh, this is the wrong opcode. We're not even... Yeah. EXA1. So I can set the opcode, but it's not parsing that yet. Cool. Oops. How'd that get there? A1. Skip key, not pressed. Not there. And that's it. Got the tests all ready. Excellent. What's wrong? 633. Oh, wait. No. Hold on. These are... Check the logic here. So, if it's less than 10, and... Oh, if it's less than 10, or... Yeah. Ooh. 619. Okay, what's wrong with 619? Key is pressed. Don't skip. Right. Key is pressed. Oh, if it's greater than 10, or that's there, greater than, yeah. Okay, there we go. Right, because checking if it's pressed, we need to bounce check. If it's not less than 10, we ignore it. The key's not pressed because it doesn't exist. Here, we check, we do the reverse bounce check, and I'm hoping Rust does shortcut. Otherwise, it'll also evaluate this, and that would be no fun. Not shortcut, short circuit. Boolean statements, because if this gets evaluated first, or this gets evaluated as well, and it's greater than 15, that's going to be a out of bounds exception, and that's not fun. All right, so that's that opcode. What's next? Store the value of the delay timer in VX. FX07. Okay, I'm going to do a similar thing for the matchup here. Well, I need this first. This would be load delay timer, right? So you're loading the value from the delay timer into a register. Am I using the right terminology here? I don't have any loads. It's all stores. Store constant. And do a register. I don't know. Load. Yeah, sure. What is this? FX 07. Right. So okay. Yeah, we can do this just fine. Just do match. Same thing as up here, because we need to match the last byte. If it's F, then we do exit delete this. Good old exit delete this. So I guess now technically anything where the second nibble can be anything, and it will be exit delete this. Oh, whoops. Match. What was it? 07? I already forgot. 07. This is what have we got? Load. Delay timer. Oh, whoops, it's just registered. Easy. All right, test it. What was that? Load in from. Okay, CPU dot delay timer. 0F. Good enough value for me. Just set that to 0 just in case. Step and assert. Excellent. Now, yeah, I think I want to get all of. I want to get the rest of the opcodes. Maybe we'll see how much time it takes. Either stubbed out or implemented, and then work on inputs and possibly graphics the next time I get to this. So we've still got plenty of opcodes to go. In fact, I could do good old test-driven development, and oh, this wasn't marked as a test, so it didn't actually run, so it might not be right. There we go. All right, load delay timer. Wait for key press and store the key in X. This is an interesting one. I'll have to think about this later. I don't know how I'm getting inputs. So, test, wait for key press. But I can put the opcode in. FXOA. So we don't need delay timer set. So here, copy that. We'll step, and then it should be something. Oh, he'll comment that one out. It's got a warning on it for us, so I know that it needs to be fixed. All right, set delay timer, set sound timer. Set delay timer. FX15. Delay timer 0. We will set V0 to F0. We will expect the delay timer to be that. Timer at 0. Oh wait, no. It's in 15. And 18 is set sound timer. Set sound timer 18. And we just replace the delay timer with sound timer. FX1E is add FX, or add register X to index, which is add index, I guess. One E. That we need CPU I. Set that to some big ol' value. And that, and it should be, I should be FAB. Fab. Of course, none of these are going to work until I actually implement them, but getting there. I is the address of this font sprite for the value in VX. I need to make font sprites. That'll be fun. That'll be a later thing. Whoops. That went poorly. Font sprite. Which is 2.9. Wait. X is, yeah, right. Because I need to load a font. I don't know where that's going to be, so make sure they're unequal just in case it does run. Binary coded decimal. Store the binary coded decimal of x at I through I1 and I2. Okay. That's an interesting one. Binary coded decimal. X33. I assume it's so you can print numbers out. You turn it into binary coded decimal and then print sprites using the digits. But anyways, 33. Let's see. Let's go there, I guess. Binary coded decimal FF. So now we need to actually check the memory. So at that should equal 2. This test can run. Five. Oh, right. 1, 2. Assuming I goes byte by byte, which I think it does. Go decimal store into I, load from I. I don't know why there's a bulk store and load, but there is. Test. Store red. I already have store register, so that might get confusing. Store bulk register. This is FX55. X is the size. Alright, so loaded from there. V0 to VX. Okay. So I need this to be something else. Do F. Right, storing it into I. So I also want to store, or I need these to have data. You know, I should really just do some sort of loop over these. Okay. I haven't actually had to really write a loop over an interval, but let's see. What are we going to put in here? 100 minus I. What's wrong here? Yeah, you know, it's fine. Excuse me. All right, and we can pull I in 250 again. No, sir equals UM plus I should equal 100 minus I. Yeah. Yeah. That seems right. All right, one last one. Load register. Bulk. This is 65. And we're just going to do the reverse here. So CPU mem of I equals 100 minus I. And we want to know that CPU VI equals 100 minus I. And these are all going to fail. What? Expected U8 found U size. Assert. Okay. That's fine. Six failed. Test add index. Yep, all the stuff I haven't implemented. Okay. So many tests. Okay. Okay. Is add index a good name for it? I can rename it later. Oh, yeah. There we go. Add index. X1E. What am I doing? Just copy this. Why do I feel like this is out of order? Load delay timer. I don't have load sound timer in here. Wait, I don't have either set. The test failures are out of order, aren't they? They sure are. Oh, whatever. I've already got this one started. What's wrong here? Expected U size found U8. That's fine. It's a U size now. Hey, that test passed. Okay. Binary coded decimal, timers, bulk loads. So, bulk loads. Skip pressed, skip not pressed. Set, delay, and sound timers. Okay. I skipped over those. Float delay timer. Wait for key press. It's the first one, FXOA. Should have just copied that. I don't know why I didn't. Yeah, that one's not actually going to be implemented. Next is set sound timer. FX15. And this one might actually be my last one. I didn't realize how long I've been streaming. Yeah, we'll get this one done first. What was it? 15. That comes before index. Wait, why do I keep not copying and pasting? Less mistakes. Set sound timer seems to have failed. Zero, 1, 8. Wait. Oh, 15 is delay timer. That's what I just did. Yeah. Delay. Copy this around. And then still check why it's not working, because it still should have worked. Okay. 0, 15. Delay timer 0. Register 0. It's F0. Run it. Delay timer should be F0. Try again. No, set delay timer still failed. Code F033 does not match any known opcodes. That's fine. Set delay timer. Left was 0. Right was 240. Oh. Because I thought I was working on the sound timer. That ought to do it. Yep. One last test failed. All right. Leave a note for myself. Next time. All right. Made a lot of progress. Got a lot of those implemented and got tests for almost all of the opcodes, except for the ones I'm not implementing right now because that involves drawing to the screen and reading inputs, and that's actually complicated. But it'll have to get done at some point. Yeah. So I think that's going to be all for now. I will see you guys later. Either with this or probably Rune Factory. The next Ace Combat game I have to figure out because while I own the game for 360, I don't actually own a 360. So I'll have to see if I can borrow one from someone or I guess buy a used one. But I'll get Ace Combat 6 played somehow. Hopefully I won't get just burnt out of it like I did 5 all the way at the end. I forgot how much of a slog that last mission was. And how much I actually really didn't like 5's story. Which just started grating on me at the end there. Anyways, this stream was about Ace Combat 5. This was writing a Chip8 emulator in Rust, and I think it went pretty well today. I actually have tests written for this thing. I can at least run individual opcodes, if not an entire thing. Alright, and I'll see you guys next time.